But as I said, it's not for any marks. I'm not going to mark it. I'll give you some time, maybe about 20 minutes or thereabout, or as much as you need, not extending more, to solve it. And then I will come back and solve the problems that I gave you in the quiz so that you know how exactly it has to be done. But before we start off, let me just complete what we started off looking at the other day, just for a few minutes, maybe about 5 or 10 minutes. And then I will put up, because I just put it up on the projection. I won't hand it sheet. You just either you solve it in your book or you have your own sheets, and you could solve it in your book and keep it with you so that it becomes sort of a reference for you as to how to do these problems. Spectroscopy, when you do experimental spectroscopy, I always have to struggle to get signal or noise, and you know where I'm getting at. So we keep the noise down a little so that we can look at the signal far better. So I'll just do a little bit of what I was doing last time. Maybe I just complete it, maybe I just polish it so that you know exactly what is to be done. And as far as this exam is concerned, all that we did after the first mid-sem. But certain basic concepts which you read all the time, that is always going to be there. You need to know that. As I said, calculation of B is not in a, the topic of the first mid-sem exam, and it should be asked now. Because when you do Raman Spectroscopy, B again comes in, therefore you should not calculate B. There are certain things that are common that you will have to know at all times. So we will look at low vibration spectroscopy, we will look at Raman spectroscopy, we will look at selection notes in Raman, we look at electronic spectroscopy of atoms, and all the things that we look at past the first mid-sem will be materials that you will need to cover for your second mid-sem exam. Do you remember last time we looked at atomic transitions? We were looking at hydrogen and we looked at helium. In the case of hydrogen, there was no big problem because all the states were a doublet S state, and there were the transitions that all to be between doublet S to doublet S or doublet P and so on. But when you look at helium, what happened? You had a situation where you could have coupled electrons, paired electrons, in which case we were looking at single states, or you could have electrons that were parallel in different states, and they belong to triplet situations. So I in fact wrote on the board in two areas, one which contained all the single states and one which contained all the triplet states. Maybe if you're talking to someone, maybe you should come here and I'll go and sit here. So that means I say something. So you're looking at singlets and the triplets, and all the transitions within themselves were okay. As far as spin was concerned, all the transitions on the other side between the triplet states, they were okay as far as spin was concerned. But you can never have a transition that's going to jump from this part of the board to that part of the board. So then in such a situation, you're actually looking at a transition from a single state to a triplet state, and we know that that cannot be allowed because it's spin forbidden. And what does spin prediction rule say? It must be delta S equals 0. Singlet can go to singlet, doublet can go to doublet, triplet can go to triplet, no issues. But you can't have a triplet going to a singlet or a doublet going to something else, quartet or whatever. That's not possible because if you have a spin changing transition, the probability is really 0. And again, where does it come from? It will come from selection rules that you have to derive by these integrals. But when you get back after your holidays and when we start looking at molecular states and so on, we will in a way look at why the spin selection rule really operates the way it does. As of now, just take it as a rule. You will see later that symmetry, actually, something we learned last time, the last semester, actually is the one that drives the singlet triplet transitions not to be possible, or spin changing transitions not to be possible. let's look at one situation. Supposing I gave you, let's say, P2 configuration for carbon. For the carbon P2 configuration, what are the states you can possibly have? For the last time, maybe if you are equivalent, if you are non-equivalent electrons, it's very easy. Because if you are non-equivalent electrons, let's say P2 is not being equivalent, it's something like saying carbon 1s2, 2s2, 2p2. That's my electronic configuration for carbon. The two electrons are in the same orbital and therefore they are equivalent. If they are in the same orbital, n is same, and therefore you have to worry about the Pauli exclusion principle. But supposing I take carbon and I promote this one electron and put it into a 3p orbital, then what happens is 1s2, 2s2, 2p1, 3p1. Now these are no longer equivalent electrons, they are non-equivalent electrons. The Pauli principle is not an issue anymore, because at least I have one quantum number that is different. If I have this situation, what are the states I am going to get when I couple the two electrons? Closed shell, you don't have to worry about it. Closed shell, you don't have to worry about it. These two, yes, you have to. What is L1? 1. What is L2? 1. And therefore, what is capital L? It's L1 plus L2 all the way to L1 minus L2, dropping it in units of 1. So it's L1 plus L2. L1 plus L2 minus 1. And that's going to be L1 plus L2 is 2. L1 minus, always write the last one. That's going to be 0. And if you have a drop in units of 1, the only other possibility is going to be 2, 1 and 0, and that's my capital L value. If capital L is 2, what state is that? If little L is 2, what's that? D state. So this must be a capital D state. A capital L of 1, P state. Capital L of 0, S state. This is S equal to half, and this is S equal to half. The single electron has spin equal to half. Then what's my capital S going to be? 1 or 0, because it can be S1 plus S2, 2 S1 minus S2. S1 plus S2 is 1, S1 minus S2 is 0. Only two possibilities, 1 and 0. What does S equal to 1 mean? It's a triple state, because 2S plus 1 is 3. And what does S equal to 0 mean? It's a single state, because 2S plus 1 will be 1. I know these are the L values, the capital L values. Now if I paste onto them the spin, what are the possible states I am going to get? A triplet P or a singlet P. So those are the two I will get. A triplet P, a singlet P. A triplet S. If I have two non-equivalent electrons, but if I have equivalent electrons, then of course we have an issue, because some of these states will not be allowed. Just like if I had helium, how many electrons are there in helium? 2 electrons. S1 equals, and they're both 1s2 electron, right? S1 is 0 and S2 is 0. What's capital S? 0. Little s, the spin is half in each case. So what are the two possibilities I'm going to get? 1 and 0. So I can get, if S equal to 0, it must be an S state, a capital S state. I can have a triplet S and a singlet S. What does triplet S actually mean? It means it's a 1s2 crystal configuration in which both electrons are sitting upwards. So it's 1s2. That would be a triplet S. And what would be a singlet S? But you know from very first principles, straight away, that this state is out. Not possible, because it would certainly violate in a big way the Pauli exclusion principle. So which means if I had 1s2 equivalent electrons situation, I know that this is not going to be possible. Even though by coupling I get that to be a possible state, in reality that state is not going to be allowed, because it's going to violate the Pauli exclusion principle. So if I have 1s2, the only state I can possibly get is going to be a singlet. Likewise, these are the states I would get if the two electrons were non-equivalent. If I take helium, for example, and instead of 1s2, I make it 1s1, 2s1. then what happens? Same states are possible. Now, triplet S becomes allowed. Simply because there are two different orbitals, there is no issue about the Pauli exclusion principle. Therefore, I don't have to knock off some states saying that this is going to make Professor Pauli very unhappy. No, because these two states are going to be perfectly allowed. 1s2 kills the state. 1s1, 2s1 keeps both of them alive. Two non-equivalent electrons, all states are possible, just like those states are possible over here. However, if I go to the ground state of the carbon electronic configuration, which is 1s2, 2s2, 2p2, what do you expect to happen? Some of these states are not going to be there. Did we do this p2 configuration in the last one or two? I thought we did. The reason I'm asking this question is I know you'll say, no, we didn't do it. I don't know that. But don't worry about it. If you have not done it, you will do it later. But I thought we did the p2 configuration. You have to write a whole lot of states and so on. If I didn't do it, I'm wrong, then we will come back and we will do it. But the question is the following. If there are two equivalent electrons, it's not going to be all possible 6 states. Only some of them will be allowed, some of them will be knocked out on grounds of Pauli invalidation. What I will do now is simply tell you which ones are going to be knocked off. We will come back after the holidays and see how they are knocked off. This gets knocked off, this gets knocked off, this gets knocked off. And the only one that's going to remain as Pauli allowed states for a 1s2, 2s2, 2p2 configuration is triplet P, singlet D, singlet S. So these are the possible states that you can get from 1s2, 2s2, 2p2 configuration. Or for that matter, from a p2 configuration. Because 1s2 and 2s2s don't give you anything. That's a closed shell. You don't have to worry about it. Therefore, a p2 configuration, whether it's carbon or silicon or germanium, it doesn't matter. As long as you have a p2 configuration, it's going to be this. Nitrogen, for example, what's the configuration for nitrogen? It's p3. But if I give you n class, what would that be? p2. So if I ask you what's the electronic configuration for n plus, it's p2. And therefore, you know it must be, and there are two equivalent electrons. Therefore, the configuration or the term states for n plus would simply be triplet P, singlet D, singlet S. Now that I have these states, of course we learned this one, I'm very sure. Which is the ground state for that among them? Between triplet P, singlet D and singlet S, which is going to be the ground state, the lowest energy state? That's the one with the highest spin multiplicity. You have heard of the Hund rule of maximum multiplicity, right? And what are the rules of maximum multiplicity say? The state that has the maximum multiplicity is the one that's going to have the least energy. And when you are told about the maximum multiplicity, it's the spin multiplicity. So of these states, which one has the highest spin multiplicity? Triplet P. And straight away you know that triplet P must be the ground state. And in triplet P, what are the substates? Or the LS coupled states, or the spin orbit coupled states? When I couple L and S to get J, what am I going to get? 2, 1 and 0. When I couple triplet P, I should get J equals 1, 0, 1 and 2. How do I get this? What is the L value for this state? 1. What is the S value for this state? Spin is 1. L is 1. And what is the J going to be for this state? L plus S to L minus S. And what is L plus S? It's 2. What is L minus S? It's 0. Therefore, I am going to get 2, 1 and 0, which we call as spin orbitals. Of these, which is going to be the lowest energy state? 0. Why is it 0? It's a state that is less than half full. If it is less than half full, then the lowest J is lower in energy. If it is more than half full, then of course the highest J is going to be the lowest in energy. So instead of P2, if I give you P4, and we know something that the P2 and the P4 have the same states. Why do they have the same states? P2 has 2 electrons, P4 has 2 holes. Therefore, if P2 has triplet P, singlet D and singlet S, P4 will also have triplet P, singlet D and singlet S as the states. So keep this in mind. So if I gave you a D2 state and I ask you what are these states for D8, it's the same. D2 and D8 have the same states. D3 and D7 have the same states. Then what is the only difference you're going to be seeing? The only difference is in the ordering of the J states. If P2 has triplet P as, let's say, the ground state, and therefore the J values of 0, 1 and 2, which is the total angular momentum, which is the mixture of or the addition of orbital and spin, that's how we got that. Then triplet P0 will be the ground state for carbon, which is about a P2 configuration. The P orbital is less than half full. But if I go to P4, again triplet P is going to be the ground state. But triplet P0 will not be the ground state. Triplet P2 will be the ground state, because for configurations which are more than half full, the higher J is lower in energy. Configurations that are less than half full, the lowest J is lowest in energy. Keep that in mind, and that's how we get up all this. So now if I ask you, what are the possible transitions that you will see in carbon between these states? Triplet P, singlet B, singlet S. And what will be the J value for singlet B? L equals to S equals 0. Therefore, the only possible value that you can get is singlet B. What about this one? Singlet S? L is 0, S is 0. Really no orbital angular moment or spin angular moment to talk about. So now if I give you these states and said for carbon, tell me all the possible transitions you will see. What are the transitions you will be seeing? Can I go from here to here? No, what's going to hurt me? S. And P to D, what is the change in L value? I'm going from L equals 1 to L equals 2. That's okay, because we know that delta L plus minus 1. Of course, it's 0, so it's allowed. But in this case, when I go from P to D, delta L is 1, because I'm going from a P state to a D state. L equals 1 in one case and L equals 2 in the other case, therefore that state is perfectly okay. That transition is okay. And let's say I go from triplet P2 to singlet D2. What is the J change? Delta J is 0. The selection rule of these atomic states with delta J equals plus minus 1, like what we studied earlier. So 0 also becomes possible in these cases. So 0 plus minus 1 is okay for delta L. 0 plus minus 1 is okay for delta J. But what do you need? What do you need for delta S? Very strict. And that's changing. So the delta S selection rule kills it, and therefore you will have no transition starting from here. Can I go from here to here? What's hurting there? Delta J is hurting. Anything else? Delta L is hurting, and therefore you will find that I can't go from here to here either. I can't go from here to there either. In other words, there can be no transition between the three states of the P2 configuration of carbon, and that's it. If ever you want to see a transition, what should you do? If I excite the carbon electron from P2 to this gives me triplet P, triplet D, triplet S. If I go to this configuration where I have removed one electron and put it in the next orbital, what are the possible states I can get? All of these. So I will get triplet P, triplet D, triplet S, triplet P, triplet D, and triplet S. How about going from here to here? Oh, that should be fine, because triplet P to triplet P, what am I changing as far as spin is concerned? Delta S is 0. I'm okay. What about delta L? 0. I'm okay. What about delta J? As long as I go from 0 to 0 or 0 to 1, I'm okay. I can't go from 0 to 2 because that would be delta J equals 2. But there are possibilities by which I can make a transition from this triplet P to this triplet P. This singlet D can go to this singlet D. So, what are the only transitions I will ever be able to observe in the case of, let us say, the carbon atom? It must be states that have been produced by promoting an electron from the 2s orbital to 2p orbital to a 3p orbital. But amongst the states that were produced within the 2p2 configuration, there can be no transitions at all, because they either violate to delta L, they either violate to delta S, or your delta J, and maybe some combinations of these, but they keep violating one or the other, and therefore you will find that these transitions will not be able to happen, and therefore you can't observe it. In fact, we call such transitions as intra-configurational transitions. What are the intra-configuration transitions? Transitions that you try to have between states arising from one given electronic configuration. 1s2, 2s2, 2p2 gives me these three states. And can I try to have a transition between these states? No. In other words, the intra-configuration transition is not going to happen. And therefore, you will see that if you want to have some transitions in these cases, you must have any one of these little transitions. But before we close this, because we still have completed the picture, there is one more selection rule on this, right? And what was that? We spoke about it in the case of hydrogen. Delta, little n. And what should that be? Plus minus 1. Now come back. What have I done in these two transitions? I've actually gone from 2p to 3p. So what is the change in the delta n, the little n? 0. What do I want? Plus minus 1. And therefore you will find we sort of felt happy that we'll be able to make transition from here to here because it seemed to be in, perfectly obeying the delta S selection rule, the delta big S selection rule, delta big S selection rule, delta J selection rule, and everything. But what is it severely violating? It's violating the delta little S selection rule. And therefore, this is also going to be a problem. If I take this and make it into 3S, delta L is taken care of because I am going from 1p to an S. Now you have to see what the states are from here and then be able to figure out whether keep this in mind that these are the selection rules. Put it on a piece of paper and bring it. You just need it. So you don't have to remember these things. And that's one of the reasons why. Because you're not using these on a regular day-to-day basis, like some of us do. You haven't learned how to derive these. Therefore, I know it's a little bit hard to keep in mind and coming to memory because these are just facts. I wanted to get out of the situation. That's the reason I'm allowing you to bring one piece of paper so that the factual part is all gone. You bring it and then use this. So if I give you a problem, consult these selection rules and see whether you can apply them. At this point in time, all I'm asking you to do is to apply these selection rules. You don't have to memorize them. Write them, bring it and see whether you can apply. And that's what is essential. When you do a full course in quantum mechanics, you will essentially derive these wave functions. And then you will see by looking at the symmetry or whatever, how these selection rules can actually be derived. Before I start the quiz, we haven't done the normal rituals, and since we are going away for a couple of time, 2 weeks or something, I just pulled out all the names and then we will go through that and also the scientists. Actually, today happens to be Proto's birthday. So there is nobody here to share it with Proto. There was one in the other class. And Proto was the one who discovered 360 along with Robert Walker and Rick Smalley. And they essentially did laser ablation of graphite and used 360 which they then detected in the market. So today is Proto. Okay. 8 is tomorrow. Kartika and Rajiv. Where's Rajiv? I better not see his signature on the attendance sheet. Shruti, 11. Yeah. I'm just reading the ones that fall into the exams, the vacation period too. 14th is Aditya and Akshay. Look, I still haven't got most of your names in my mind, so you have to raise your hand. Who is Aditya and Akshay? Okay. And 17th is Vaishnavi. I still don't see the Vaishnavi is not here. Oh, okay. So these are the 4 I could work with. And of course, when we get back, we will continue. Except in the last class, I stopped with whatever we. Because I stopped teaching that from this week onwards. They start doing inorganic when they get back, and suppose we take over. Start doing the organic. So it will hard if you are beyond this, you just have to find out where it's there. Okay, 8:10, that's tomorrow, is actually a very very important person in chemistry whom you have seen, or whom you haven't seen, you have heard, studied about it. You will like it by getting to see. It's Deschamps. The Deschamps organism. And of course, there are very many pronunciations. I went to check out one thing. It's a French guy, so the pronunciation has to be out of the ordinary. And it's pronounced, I believe, as Le Chapelier. And